So now we're going to talk about another use for dimensionless analysis, and it's in experimental systems. So when you look at the dimensionless equations for incompressible flow of a single fluid, and by a single fluid we mean we're not dealing with a situation where there are an air-water interface such as waves on the ocean or anything like that, or some fluid inside another fluid. If we have a single incompressible fluid, then these are our equations that we showed we could derive in dimensionless form. And what you can notice right away is that there's only one parameter, the Reynolds number. There's not, mu and density and all of that are all, boiled down to just this one parameter, the Reynolds number. What that implies is that flows that are geometrically similar, there's only going to be one parameter that differentiates between those flows. So if we can solve a problem that is for one Reynolds number, it will apply to any solution that has that same Reynolds number, in this dimensionless form. So what that means is if two flows are geometrically similar, they have the same solution. So I'll say all flows that are what we call geometrically similar and that have the same Reynolds number have the same solution. In dimensionless terms. In dimensionless form. So what that's going to allow us to do sometimes is to model something experimentally and get an experimental answer for a system by testing a different system. So why would you want to do that? Well, for instance, if you had a system that was particularly large, maybe too large to test in a lab, practically, maybe you could test a smaller system, a lab-scale system that had the same Reynolds number and was geometrically similar. And that's one of the main uses for this, is to try to come up with situations in the lab that accurately give results for systems that for one reason or another cannot easily be simulated in the lab. Obviously, this would be an example would be flow over the hull of an airplane. Yes, there are some giant wind tunnels out there. I think Boeing has them, but they're pretty hard to use for something the size of a massive Dreamliner or something like that. So a lot of testing is done at smaller scales. And the question then is, how do you apply those results from smaller scales to larger systems? And this is a big part of how you do that. If you match certain parameters, geometric parameters, and Reynolds numbers, and as well as some other parameters in the case of airplanes, but you can often use experiments on much smaller, more modest systems and get accurate results for different systems that are, as I say, some reason difficult to test in the lab. So we're going to go ahead and look at how you may do this for a very simple system in the next lecture. But remember, one of the reasons that this is so important is that we know that a lot of our results that we've been using for turbulent flow in particular are derived entirely from experiment. So the fact is that we don't have drag coefficients or friction factors or lift coefficients without running experiments, and we can't run experiments on things like full-size airplanes. So we're going to need to have ways to test those things without simply building airplanes that won't fly and then failing to fly them and seeing why at full scale. Obviously, there's a big incentive to try to get something that's a smaller scale, more reasonably approached system that will give us valuable experimental information about fluid mechanics for those systems.